Okay. All right. Can you hear me okay, everyone? Yeah.
Jale says much better now.
Oh, okay. Oh, Jale. Okay. So Jale is thanks, Jale. Good to have you with us. So Jale is a PhD candidate with us and actually working with carrier project on a carrier project. This forum is on healthy buildings for people and looking at a multi-scaled approach for improving indoor air quality. And we have two speakers today, and Mike is going to introduce the carrier program first, and then I will follow up with a presentation talking about the multi-scale strategies for IAQ improvement. So without further ado, let's welcome Mike Buncroft. Thanks, Mike.
All right. So my name is Mike Bruncran. I work at Carrier, and a little background of Carrier. It's a $35 billion company, publicly traded on the New York Stock Exchange, with about 50,000 people. And our focus is on building systems. So how do we provide the safety and comfort for the occupant? And when you think about the occupant, it could be a family, it could be an individual, it could be the people in the room. It could also be, in the case of healthcare, the patients. So as we think about all the different areas that our equipment is applied, we started to step back and say, okay, from the perspective of that end receiver of that safe and comfortable environment inside the building, really, how do we start to even design our equipment to meet those needs? And that really started the whole healthy building and healthy home movement within Carrier. And the pandemic has really shown a light that the air that we breathe is really important to us. It's not only something that we are, when we think of our AC unit, it's not only that, oh yeah, the temperature's hot or cold, it actually impacts our health. And so there's many studies been done previously, but really the pandemic has shown we have to take care of the air in order for our health to be one of the key things that we need to focus on. So I always like this statistics that if you think about the amount of air you breathe in a day, it's about 20 pounds. If you compare that to the amount of food or water you drink, that's somewhere between 3 and 5. So you breathe in way more air than you eat or drink, and yet we don't think about it. And so the whole idea of the healthy building program is to look at, okay, what is going into your body, and then focus on that air piece, which people really don't have control over. That is actually controlled by the contractor or the building facility manager or the construction group that is putting up that building. And so as we think about that, we have to say, what can we do in order to improve the indoor air quality? And so the research that Jensen and his group has really focused on really started to shine the light on what is that strategy that we need to develop. And when we think about it in terms of a monetary value, this is healthy is a $7 trillion market opportunity to us. And part of that is healthcare, and part of that is individualized medicines. But then there's part of it that's going to be upgrading your building, upgrading your home in order to take care of your health. And so, and keep you going. And so that really has started the Healthy Building Program at Carrier to say, given the needs of the people, how do we get there? At the stage, I'll give you a little bit of a little doom and gloom right now to explain why healthy, though there's this big target of $7 trillion, why that path is not clear. So you have right now supply chain issues, rampant inflation that's been really hampering a lot of decision making. And then we look forward, and that's affecting people, right? That's affecting your ability to purchase. That's affecting your ability to decide what you're going to do in the future. Now we look forward, and for buildings, there's going to be a DOE minimum efficiency for HVAC equipment. There's going to be a series of decarbonizations, changes to the regulations and codes over the next 9 years. And so you're seeing that, and you're seeing, okay, now we have the CoE Amendment, which has been ratified. That's going to start kicking in 2024. All of these events are really clouding the picture of healthy. But if we lose sight of delivering healthy, clean air to people, then we lost sight of that end recipient of all the work that we're doing, all the reason that we're building this equipment. And so the Healthy Building Program really is making sure that we maintain that connection to the end recipient of that clean air. And when we start breaking it down and saying, okay, Jensen's research really has shown us a way to look at what is the strategy that we could take forward as being a model that could be applied not just in one region of the country, but globally. When we talk about ventilation and saying, hey, we just need to increase ventilation, that's great if you're in a moderate climate. But if you're a school in the upper northern regions of the US, that doesn't apply because they have been using radiant technologies and Univent for the last 30 years of their construction. So their buildings are not set up to bring in fresh air. If we look at the southern regions, yeah, that's great. We can bring in more fresh air, but then we're driving up the cost of and energy efficiency of operation. So when we start to look at what is that right balance, then if we start to say, okay, we just need a layered strategy, and we need to start bringing in different technologies and allowing the building owner to evaluate these technologies as being an equivalent one-for-one, then they can make the decision on how best to tailor the application of the technology into their building in order to provide that clean air. And so if we start with this layered strategy and start building up work that we've been doing with Shelley Miller and the group down in Colorado University, really has started to say, okay, what's the relationship between the disinfection, which the cleaning of surfaces, and how does that relate to the removal of viruses and pathogens from the air? We could see that they're about equivalent. So now we have to, so then we start backing up and start and say, okay, our layered strategy fits into this larger layered strategy of cleaning, disinfection, and so it makes more sense to approach with a multi-scale strategy than just saying, hey, we're going to demand ventilation or we're going to demand one technology over another. So we're starting to see that there's a whole bunch of equivalencies that can be made, and that's really exciting to see, because where we want to go in the future is more towards an approach that we have the flexibility to address the problem, and so with that approach, we're going to get into the science of multi-scale strategies, but with that approach, it allows for us to explain to a practitioner, not a researcher, or not another indoor air quality company, but to an actual practitioner who is out in the fields. They're dealing with maybe 4 or 5 different fires, none of them related to indoor air quality. We're able to explain to them how they can apply indoor air quality solutions to solve their problem in the context of all the other problems that they have. And so that really is the next step in adoption and making sure that this healthy building, healthy home trend continues to grow. And today the gap of the practitioner, the OEM, and the researcher, there's still large divides. And so with the work that this community is doing, I mean, this is very exciting to be at the forefront and at a point where we can make that jump. It's just a little bit more effort to get there. With that, I'll turn it back to Jensen. Thanks.
Thank you very much, Mike, for your comments and give us an overview of what the Carrier, healthy building program is about and why, why we are looking at indoor air quality research. In particular, I think your comment about how can we make the technology applicable to practitioners, and that is really important. We do a lot of research. Sometimes we get offside, about the application side. So working with engineers who are doing day-to-day design of the HVAC systems and for different type of buildings and how to improve the air quality in energy efficient way. I think that's continued to be an important problem. So we will have even more time later for questions and discussions. And I will give a quick overview of the multi-scale strategies that Mike alluded to for improving IAQ and also reducing the risk of infectious disease transmissions. So I'll try to cover sort of 4 areas. And first, and perhaps for most of you, maybe just a review, okay, talk about an introduction, a 3D view of indoor air quality. And then I would move into talk about what are the potentials of current IAQ control strategies. IAQ research has been done over the last 40 years. Actually, it's not something new from research point of view. But what kind of technologies are available? What's the potentials of these technologies? And then I will talk about the integrated approach and probably giving focusing on this layered approach that Mike mentioned to mitigate the risk of airborne infections of COVID-19. And I do have another example, which is basically specific talking about this particular building, how different technologies has been applied in integrated for energy efficient IAQ solutions. But I may not have the time for that, but we will have maybe another sessions for this. And at the end, I will touch upon the future challenges in IAQ research. So why study indoor air quality? So we have this, in my mind, I look at the climate, buildings, and the people. We do everything for people, right? Human health, performance, and well-being. But at the same time, we want to watch we are not damaging the climate more than we have already done, right? So, but building is an important component because we live in buildings, people live in the buildings. And you can see these interactions, the climate impact building. Of course, climate and building impact people, and building and climate also interact because building consumes a lot of energies, and those energies is equivalent to a lot of CO2 emissions, which will change the climate. So we have these 3 things actually interacting together, and we need to look at the human health, performance, energy security, and climate change, and also the indoor air quality now because of in particular because of the pandemic, COVID-19, that we need to pay even more attention to the indoor air quality, because that can help us to mitigate the risk of current pandemic, but also prevent or minimize the risk of future pandemics, and which supposedly what they've been as predicted is to have more this kind of event coming because of the climate change. So now if we look at the built environmental systems, and this picture, I always like to show this picture just to show that, you know, there's a healthy, what we are looking for is a healthy indoor environment, but it's also in harmony with the outdoor and natural environment. From this picture, we can also see the different scales. And we have scales around the people in the room scale, building scale, and urban and even larger regional scales. So that is what we call the multi-scale nature of the built environmental systems. You know, from personal scale, micro scale, look at 0 to 1 meter, and the room scale 1 to 10 meters, and the building scale 10 to 100 meters, and then we have 100 meter to 10,000 meters outdoor, you know, around the buildings, basically city scale or neighborhood to city scale. And then we have the even meso scale, right? So regional scales. And these scales are, what I mentioned, are spatial scales. At the same time, what's embedded there is also the time scale or temporal scale, because that has a lot to do with the dynamics. For example, you know, if you look at the environment, the condition around us, that probably happens. You know, if I have a personal air jet coming to me, in a scale of seconds, right? But room scale, you have air supplied from a diffuser come to you, probably in a minute scale. But if you look at the outdoor temperature change, we have a daily scale. So again, then you have a seasonal scale. So these temporal scales are interacting with the spatial scale, and which we have to look into in our strategies for improving environmental quality. We can apply many different strategies, you know, at urban scale, urban planning, source control, pollutant removal, energy sharing, and we can look at the building scales, HVAC system, envelope, material selections, and the room scales, and even micro scales, personal ventilations, smart furnitures, micro wearable devices. So as we refine the control from larger scale to a smaller and smaller scale, and then we have the possibility to enhance or improve the occupant satisfaction to 100%. It's actually very challenging to do that, you know, because right now the industrial standard, the design standards, like ASHRAE standards, the design goal is to have 80% of people satisfied, right? If you go to a car dealer, you want to buy a car, the dealer tells you only 80% of people are satisfied with our cars. You probably won't buy it, right? So, but why we are doing this? Why this building industry is still looking at this kind of standards? That's because I think there's two things in my mind. One is that everyone has a different preference on the conditions they want, right? To tailor the environment to individual needs, and it can be very costly, and we don't have a very good way to do that yet. So one is the need, the other one is the cost we have to deal with, economics. So those are the two things that creating some barriers and challenges for us to reach to 100%. But it is possible if we tailor the environment, find a way, a clever way to do that, it is possible. So the built environmental system is a multi-scale system, and we can look at it as like a control system, which has goals to improve IEQ, energy and safety and security, and then we have multi-levels of controls to achieve that. There's a very high level, multi-scale nature of the built environmental systems. Another challenge we have are dealing with is called a multitude of pollutants indoors. You can see here a variety of pollutants. We categorize them into two big areas. One is the gaseous pollutants, and then particulate pollutants, and the two also interact. Like a semi-volatile is a gas, but it's absorbed on the solid particles a lot because of the low vapor pressures involved. And then we are dealing with also biopollutants and other radioactive gases and so on. So there's many pollutants we are dealing with. And of course, one of the things we are facing is the virus, right? Right now, pandemic is not over yet. So that's again posing another challenge. How do we deal with this different variety of pollutants? Because there's no single technology that can work for all the pollutants. So we have to look for, a combination of technologies to deal with different types of pollutants. And of course, these pollutants can come from, a variety of sources, and I call it multitudes of pollution sources that we need to deal with, either from humans' activities or building materials, machineries, and so on. And they can come from indoors and outdoors. So the fundamental principle of pollution control is simply that trying to prevent the pollutants from sources, whether it's outdoor, indoors, and to get to the people. That's the very high level. And we look at the outdoor, indoor pollutant sources, whether it's from people, materials, equipment, or reactive components. And we have three control strategies there: source controls, ventilation, and air purification. So the 3D view of indoor air quality engineering is the three dimensions. One is about the spaces, multi-scale spaces. And another dimension is multi-species, a variety of pollutants. And then the third one is strategies. So we put these three dimensions together, it will give us a 3D view of this problem, and which will help us to identify technologies or strategies to mitigate the IAQ problems. And there's some more detailed discussion. What I'm presenting here is in this most recent chapter that my collaborator, Jia Lei Chen, who is a PhD candidate, and my collaborator at the Nanjing University, and we have actually wrote a chapter here called Managing IAQ at Multiple Scales. It's published in the latest Indoor Air Quality Handbook, so it's available for that. But I will give you a sort of very overview of what's in that in this talk. So how do we manage IAQ at multiple scales? So we talk about the scales: micro, room, building, and urban environment. And then we talk about different control strategies: source control, ventilation, air cleaning. In addition to this, we added the called moisture control. It's very important. Okay, that moisture has interaction with a lot of air pollutants, whether it's adsorption, desorption, and biocontaminants. So it plays a key role, and it's related to the local temperature and humidity controls. So that by itself can be a separate topic to discuss. Okay, but today I will be more focusing on the first three strategies. As you see from this table, we can apply these strategies at different levels. Let's just look at the room level. For example, we can look at the indoor materials emissions. How can we reduce the emissions? And then we have to watch about the chemistry, indoor air chemistry. If you have air cleaners that using catalytic oxidization method to clean the air, it's okay. It's a technology that you can apply, but you have to watch for the potential byproducts coming from that. You may have to devise some filters to remove those the ozones generated to avoid secondary emissions. And of course, the room air cleaners and room ACs for humidity controls. So I will briefly talk about the different scales and what kind of technologies are available, how effective they are. And this slide shows at urban scale, right? So we have, for example, introduce more fresh air and fresh air for the city. So now ventilation is not just building ventilation. Actually, we are talking about city ventilation. It's impacted obviously by the building geometries, and there's a lot of emissions, source emission for transportations, and urban greening, air cleaning, and also large-scale air cleaners even has been used. So if I give you a few examples, well, the pollutants we are dealing with urban scale, PM 2.5, ozone, NOx, SO2, and VOCs. At urban scale, ventilation, for example, we can plan the city, design the buildings so that it can allow the wind to go through that areas to provide sufficient ventilation for the buildings area. And even there's a local air cleaning strategies, local exhaust, the pollutants from the traffic, exhaust out, all provide clean air through these channels to the local street levels. So there are these kind of technologies that or strategies that can be applied. And even at very large scale, huge air cleaners, air cleaning towers that has been developed. This was in China. There's some research going on in this area. And we can greening vegetations, grasses, shrubs, trees, and we can look at the building envelope, how to use building envelope as a cleaning mechanism. And imagine you can coat the building surfaces with materials that actually decompose volatile organic compounds under sunlight, like UV. There's always UV there. It's actually very effective energy to use for cleaning. So these are two examples. Then at the building level, we are probably more familiar at the building level, ventilation, source control, and air purification. And again, I also show a few examples here. First one is managing, this is, I show the three strategies here. So first is the, this is overview of the slide. So we talk about this ventilation, supply 100% outdoor clean air, all cleanly recirculated air, right? And we can have integrated ventilation and air cleaning and apply model predictive controls, okay? So there's the 5 strategies I listed here, but in the interest of time, I probably will only talk 2, show you 2 examples here to see, okay, how effective they are. Right. So one is biofiltration and ventilation, and this is also a project that was we worked with industrial partners that look at how can we use the plant's root system. It's not a plant leaf. Plant leaf has very low purification capability. It's insignificant. Okay. But if we pass the air through the root system, and that root system also has the activity carbons and moisture to absorb the volatile organic compounds, and then those VOCs then became the food for the microbes in the root plant. So in this system, the microbes will regenerate the bed for purification. So we don't have to replace the carbons and so on. All right, so that system was developed here. And we actually run a demonstration test using an office space and plugging this air purification system into the recirculation loop of the HVAC system. And we can see how effective they are in terms of, first of all, single pass efficiency for formaldehyde and toluene, for formaldehyde and toluene. And you can see that the single pass efficiency for formaldehyde stayed around 70% over a 60-day period. So this is a fairly long time test, actually. It's very few tests that has run such a long time in the full scale, in the actual space. And then you also see the toluene. For toluene, is not as effective, but still have about 30% efficiencies. And the question is, okay, if we use this air cleaning technology, how much energy we can save, right? The principle is that because formaldehyde has a very low threshold limit for indoor concentrations. So if you want to use ventilation to dilute it, you need a lot of outdoor air, and then which means a lot of energy to condition those outdoor air. But if we use this air purification technology, we can remove formaldehyde, and so that we can reduce the outdoor air supply by 80%, which is give us 15 to 20% saving in energy. So that's the relationship of between the air cleaning technology and energy saving for the buildings. Second example was called integrated ventilation and air cleaning strategies. So in this diagram, you see this is air cleaners integrated into the recirculation systems of the air handling systems. So in this integration, we would look at, okay, what are the needs of the indoor conditions when people are in a building? When people are not in a building, we don't need to ventilate as much. And then we also look at what's the outdoor conditions. And when the temperature and humidity is right outdoors, we can use free cooling. Use outdoor, has more ventilation and for dilution of pollutants. But when outdoor air pollutants is high, we cannot do that. So we have to either activate the air cleaners or reduce the outdoor air intake. So there's a different combination of strategies: outdoor air ventilation, air cleaning, or recirculation flows, and as a function of outdoor weather and indoor demands. So in that, and with the simulation using this building as an example, we actually were able to see the benefit of this approach, and it basically significantly lowered the concentration due to dynamic integration of ventilation, lower by 40%, and without at the same time improve energy efficiency. Now at the room scale, IAQ strategies, I show the overview here, and again, source control, air cleaning, and ventilations. And the example, we start with the source control. Source control means reduce the emissions from various building materials. An example here I show is the furniture. Furniture industry that we have worked with furniture industry, which is represented by BIFMA, called the Business and Institutional Furniture Manufacturers Associations. And we jointly developed a standard, and now it's a national standard, ANSI national standards for certification of furniture, low emitting furnitures. So any materials that pass that standard would have a low emission, which means we reduce the load of pollutions indoors. So that's a source control. And the second one is called effective supply air or ventilation. We want to deliver the air to where people are. And then third strategy is effective room air cleaning. So I talk about these furniture emissions. Actually, there's a standard. There's a different standards about furniture emissions. And through this standard, we were able to unify at the end what should be the threshold and how the furniture should be tested. And you test the component or system. You can do either way, but there's a model, mathematical model allow us to look at overall emissions from different furniture components. Then on the source control side, we also need to watch for the secondary emissions. For example, if you have ozone, whether it's introduced from outdoor or generated indoors, that ozone can react with the skin oil and to generate additional pollutants, and that's what we don't want. So in this particular study, a collaboration with Purdue University, that we place a box that's simulating the human body, and a heated box, and then we put this the T-shirt on it, warm T-shirt. After a student wore it for 24 hours, put it on, so there's skin oil, and then we introduce the ozone into this chamber, and you can see that from this chart here, this is the background conditions. These are two tests shown here. So the background versus when the ozone is present. So you can see the increase of the pollutions. And that's another test. And the low ventilation conditions, 0.5 ACH and 2.7 ACH. And the important thing is that these products, many of these products are very harmful to people. It includes formaldehyde, which is a carcinogen, a major indoor pollutant. So we definitely want to avoid these secondary emissions as we trying to find ways to mitigate indoor air quality problem. For example, using air cleaners, we want to avoid this side effect. And then in terms of ventilation, we know there's a typical space, there's a lot of mixing type ventilation, and also displacement ventilation and personal ventilation. The principles are basically three things. One, we want to deliver adequate amount of air and deliver the clean air to occupants, and it's also this air can remove pollutants, dilute the pollutants. Okay. So deliver clean air only to where it is needed. Air purification, and it can be applied at many different levels: outdoor, cleaning outdoor air or recirculated air. And in this case, at the room scale, we're talking about standalone room air cleaners and also the passive materials. And for example, gypsum wallboard. There's a new kind of gypsum wallboard that was made in France. I don't know you know that. Actually, they have in the manufacturing process, they have a coating on it that actually can absorb and remove formaldehyde and toluene. So those are things that new products coming out, the passive materials. And there's also on the new research looking at the metal organic framework, we are collaborating with Danish Technical University and also a university, the Normal University of Paris, in looking at the possibility of using MOF materials, metal organic framework materials for both moisture control and coating and for air purifications. So there's some, we call them passive materials, which does not consume energy, but can purify the air. So that's another area that we'll be investigating. So I've shown some air cleaners we tested before and give you some sense of the CADR values that was done. This was the 2005 study. We have a new study coming out soon that look at different air cleaners and how much clean air they can deliver. So this horizontal axis here is called CADR, means clean air delivery rate. It is like effective or equivalent ventilation rate that air cleaner can provide. And however, it's targeted for the pollutants that air cleaners are effective with. So we cannot use that to replace the ventilation entirely, because ventilation air is non-discriminative. Any pollutants, it will be diluted. But air cleaners only works for certain pollutants. So CADR, we need to recognize that that is for specific pollutants only. Okay. So this shows the amount of can provide. And here only show like about 50 to about 50, like a 50 CFM. So how much is 50 CFM? You know, and if you look at the a 50 CFM, you know, using actually standard as a guide, so 50 CFM can cover about 200 square feet, and for about 5 people, basically, in open plan office. But if for private offices, basically can provide clean air for 2 to 3 people. Just give you an idea what the air cleaners, effectiveness of the air cleaners. The newer air cleaners, if you buy, let's say for the COVID, you know, for reducing the risk of COVID-19, and now you can see the air cleaners are designed bigger and bigger, you know, higher airflow rate and higher clean CADR. You can get to like 150 to 300, which is you can get from market now. Okay. And certainly we can also apply the strategies at as personal scales, and this I'm showing some like at what are the goals and the strategies at personal scales. And there's a major challenges at the personal scale. There's 2 major challenges. One is about the minimizing the mixing between the clean air and room air. So if you look at a small jet here, it shows a clean air jet coming out to the room, but before it reaches to the person's breathing zone, it's already mixed with the air. And that's just nature of the air jet. You know, when you have an air jet, it mixes with the ambient air. Okay, so how can we prevent that? How can we deliver that to the person? Right, that's a challenge. Another one is remove the pollutant brought with the thermal plume. And people generate thermal plume, and we actually have drawn air from the bottom up. So the emissions from carpet, for example, actually rise with the air we're breathing. So those are 2 things that we need to be looking for. But the performance of the personal ventilation can be modeled and tested. We can see that personal ventilation does have a higher air quality index, you know, compared to underfloor air distributions. So it is more effective. And if your jet is close enough to the person's breathing zone, you can actually have a good clean air provided. And in one of the studies, we actually tested 4 different air diffusers. One is underfloor air diffuser, circle here, and the personal ventilation, and also chair ventilation. You have this air supplied, you know, through these tubes, yellow tubes, and then it's rise with thermal plume and get to the breathing zone, and to see how effective they are. And this was an invention from Denmark, actually. Professor Nielsen's team invented that, and he was a visiting professor here, and we tested here. And using a thermal mannequin, as you can see here, the thermal mannequin is simulating a person that generates the heat, and so we can simulate the thermal the plume as well. And using the TIEQ facilities upstairs in this building. So what you see here, just very quickly, you can see that the effectiveness of this called efficiency. Okay, efficiency, ventilation efficiency, local ventilation efficiency, and in general, basically, personal ventilation can improve IAQ by a factor of 3 to 5, you know, because of the local air supplies. Another technology that was developed by Professor Dan's group, early on, is a local exhaust, local suctions, and basically this was developed for the airplane applications. That you have a, these are let's see. I'm looking for, okay, here is where the typical air distribution in air cabins. And if we take a small part of this air, okay, and have to locally exhaust this, okay, so total amount of air is still the same, because we want to make sure energy consumption doesn't go up. So, but just take a small amount of air locally, you suck that air, and you can see the impact on the pollution control. On the top of this graph shows just regular conditions. So you have the three people sitting here. If this person has let's say, have a SARS virus, and you can see these pollutants actually will quickly transport to the adjacent person. But if we apply this local suction, you can see this pollution is very well contained. There's a much less transmission to the other people, the adjacent people. And if you have another strategy is overhead suction instead of the side suctions, and even more, this technology is more effective. So the source, all those viruses are contained here. And they actually test this in the mock-up, a full-scale experiment here. I think one of the former student is working for Carrier, Ryan Dykers is working with Carrier now. So we can manage IAQ at multiple scales, and what are the potentials and limits. So based on the existing studies, and we can actually, we have a range of numbers that show how effective they are. This table basically shows the effectiveness at different scales in terms of source control, ventilation, and air cleanings. And now then question is, I think what Mike alluded earlier, well, each technology has certain effectiveness. How can we integrate them into so that they are most energy efficient and effective, and especially tailored to different type of spaces. Schools are different from office buildings, hotel, restaurants, they have different systems. So we need to tailor that into the strategies differently for those. Now, so the case one is the IAQ in office building at Syracuse. That this is a multi-scale, test bed we're trying to develop here. So we have urban scale, building scale, room scale, and the personal scale. And in this particular example, we look at COE, Syracuse COE headquarter buildings, and in which we actually applied these several source control technologies, including like removing traffic emissions. For example, if a highway I-81 has been changed and there's much less traffic pollution on that. This is, of course, has not happened yet, but we can model and simulate that. Right? And low emission building materials and the low emission furnitures. And in terms of ventilation strategies, we can look at there's a first floor lift up design. There's a 100% outdoor air, mechanical ventilation, also natural ventilation using by opening windows, that's possible, and underfloor air distribution. It's based on demand, demand controlled ventilation and personal ventilation. So these are also can be implemented here. And then we also have air cleaning strategies here, green roof at the urban scale, and high efficiency filters and standalone air cleaners. So these are all the strategies that can be implemented. Some are already implemented in this building. But we can evaluate them to see how effective they are for different pollutants, PM 2.5, ozone, formaldehyde, and infection risk, infection probabilities. And what you see here is that the gray bar shows the baseline. What is baseline? The baseline is the condition based on actually design standard. That's the baseline. Okay. Then how much improvement we can have? 89 to 90% for PM 2.5 if we introduce apply those strategies. For ozone, relatively little change we can make because we are already using 100% outdoor air ventilation. So the ozone coming from outdoors mainly. So not much we can do if there's ozone there. Formaldehyde will reduce the emissions, and the infection probability we can reduce by about 80%. So if we apply those strategies, these are the potential, and the limits we can do. The second example is about the strategies applied to mitigating the risk of infection of SARS. And this is a collaborative project with Carrier. That again, the paper is published in this another paper. And here I just show a summary of the results. So if you look at the strategies we have building, breathing zone scale, right, personal scale, room scale, and building scale. And we also can rank different strategies in terms of the cost of implementation, low cost, medium, high cost. So these larger circles means the reduction of infection risk effectiveness is higher, right? So this is like 100%, and this is very, very effective. This is displacement ventilation plus partitions. Combining these two strategies, we can achieve very good reduction in risk. However, the implementation is difficult, relatively difficult, because you got to design the airflow very carefully so that the amount of air provided to the person is equivalent to what's been drawn by the person because of the thermal plume. And so that is something we have a strategy on that. So this is one technology we are developing. But right now it's too expensive to implement. This is low cost, most effective. That's masking, right? So mask, obviously, is very effective. And working on the breathing zone, it has two functions. One is reduce the emission from the source. If someone has carried the virus, there's less emissions. The second function is also filter the air out. So it's a cleaning, filtration functions. So that's why it's relatively effective. And at the building scale, we talk about the reducing the occupancy, obviously. And when you reduce the occupancy, the ventilation per person is increased. And therefore, there's more dilutions and less transmission between the people. So just quickly as a summary, and we can integrate strategies, in terms of emission source reduction and personal air delivery and local exhaust, local air purification, and also we can integrate ventilation, dynamic ventilation and air cleaning. And then the last one is apply intelligent control strategies, which can, basically enable optimization based on dynamic outdoor and indoor conditions, including occupant activities, and apply model predictive controls. And this has a lot of potential. In fact, when I reflect, everything we do, if we can plan and predict better, we can actually improve our performance. It applies to air quality control, energy efficiency, also apply to many sports activities, as you can see. So as you walk in, we have a ping pong table downstairs. So after this, you are welcome to try it out. Any game like ping pong, if you can predict where the balls come, you can, you can perform better. So model predictive control, and that's very, I think, effective, and we can all experience that. Now, last slide. This is my last slide. Sorry, take probably a little bit longer than what I planned for. But I'd like to just say, what are the future challenges in IAQ research? And I listed 6 of them here. One is quantification of IAQ benefit. IAQ, everyone knows indoor air quality is very important, but it's how to quantify that benefit. It's still something that we don't have very good index yet. Okay. And better IAQ, which is a better IAQ metric, leads to that. And then better IAQ sensors, occupants' behavior. I mentioned the model predictive control. And lastly, the social, economic, and the environmental impacts. We also have to investigate and quantify that. So with that, I'll be happy to, I'll invite Mike to join me, and then we can answer any questions you may have or suggestions. And
Mike.
Yeah.
Yeah. What are APAs
Can we come over here?
to incorporate air purification, humidity, air filtration? Everybody has to put them in separate with them at great cost. Where are the manufacturers being able to integrate these things into the furnace HVAC system?
Do they want to repeat the question?
You could summarize that.
Yes, so the question is, where are the equipment manufacturers in being able to take indoor air quality principles and integrate them into the equipment? Correct?
Right.
Okay. And so pre-pandemic, I would say it was very much a specialty type of water. And so when somebody wanted an indoor air quality feature or product, you would actually have two sets of specifications. You would have the equipment, and then you would have to specify the indoor air quality equipment that you need. And that's very expensive. So pre-pandemic, I would say dollars per square foot for an indoor air quality solution. As the pandemic rolled in and people got a sense that things needed to change, it's now into the range of what we would say sub-dollar type of solutions per square foot. Where do we see in the future? Clearly, in order for us to drive up the adoption, we need to embed more of the technologies into the standard way that we both specify as well as build the HVAC equipment. And so, and then as we do that, we expect the solution costs to go down. And so that allows a larger adoption and a more broader application, because if you're scaling to more of the population, you want the solution readily available at a cost that can meet their needs. And especially in this time, it's very difficult to say, hey, for a premium product, when inflation is going at 8% plus, why would you want to make that choice? Well, in the future, as we go to embedded solutions, you now don't have to make that decision. And so I would say that's the direction, but we're on this road to get there. We're not there yet. And if we think about when we're going to look for opportunities to really go for embedded solutions, you have to look at what's happening within the buildings. There's two schools of thought. One is on energy efficiency, and the other is on increasing the ventilation for cognitive benefits. And so in the future, what Jensen, his research is looking to do, and others, it's really to say they're not mutually exclusive. What you can do is you can look at indoor air quality as a way that you're still focused on that end user, that end recipient of that clean air. You're just redesigning the HVAC system in order to provide that air in a more efficient fashion. And so that's the changeover. We haven't gotten that mindset down yet, and in the practitioner level, but that's the direction we want to head.
So I kind of heard that you're looking at pushing that not only indoor air quality, but part of that solution would include bringing in more fresh air, which of course would be counter to the aspect of heating and cooling that air, conditioning that air. Are you looking at as well as integrating some kind of heat exchanger function in units as well?
There's many different approaches to conditioning the air, and so it's very difficult to pin down one and talk about it. But what you can explain is, as you bring in more air, you're going to have a higher load, right? So now you have to balance that load with the needs inside the building. What you can start looking at is, okay, do we need all that air all the time? And most buildings are over ventilated based on their occupancy. So now we start bringing in these other layers of continuing to focus on the occupants inside the building and understand, okay, what are they doing inside the building? How many people are there? What is the activity level of those people? What is the air quality that is needed to be provided to those people? And when you start doing those type of calculations and then building up from there, ASHRAE 62.1 is a great example of a standard to help with that. You now start building up this idea, okay, there's now a way for us to move forward with providing that clean air and saving the facility manager and the building owner money.
Of course, that's something more, a whole list of buildings, smart building approach. Conference room, like the first space conference rooms, I'm not heard about it. What about, are you familiar with any solutions where you can provide clean air, eliminate VOCs, reduce particulates from out and put some outside?
Yep.
Your transit does it all the time with friendship with the bananas. You lock them in, and if you lock people in the building, you have to sense the pollutants. You can either absorb the pollutants, then you're working your way towards a submarine. It's a difficult thing to do. I think getting there can happen, but it'll happen if you were to flip back to Carrier 50, 60 years ago when Willis was still around, about 70 years ago, and the industry was being created. There were many custom systems and all of the filters, all of the humidity control, all that stuff was in there. But it was a capital investment. Today, everything is separated except for your own home. You own it, you bought it, you run it, you pay for everything in it, so you can influence the decisions. In commercial buildings, it's very hard to get all the players together to agree ahead of time what to do, and then thank God if they actually run it the way it's designed. Which is something we saw in the presentation, and what Ian brought up, the actual system operation can be a bigger penalty on both health and energy than a bad design. Bad operation can be worse than bad design.
We agree with you.
Absolutely.
Commissioning and then making sure your equipment is operating
properly for the building. Number one area that you can save energy and provide healthier air. Then you go into, okay, what is the equipment upgrades that you need to get to the healthier? That's step two. Making that assessment to determine what is the future capital upgrade you need to make based on your needs. Then finally is this step three, which is really about how do you sustain those upgrades that you've made in order to continue to monitor and inform yourself of what the air quality is inside the room and how your HVAC system is performing. That way, you're looking at it from the building level. You're saying, okay, now we're managing our building really close to that energy efficient envelope while providing the healthier air.
Perfect. Give us sensors that don't need calibration on a yearly basis. And give us strategies that can take the data input from the sensors, knowing who's in the building and what the building is being asked to be done so that the HVAC equipment can respond appropriately.
Well, that's like density. They're $1 billion valuation, right? So they are benefiting from what's happened with COVID in the workforce environment and trying to adjust occupancy and density to deliver heating and cooling and air purification. Professor, you might be interested to know, I just got a notice that the World Health Organization has just banned gas stoves. And California already now, all right, has a regulation that new homes cannot be equipped with gas stoves. The methane leaks, right? And my daughter, who has 4 of our grandkids, is so proud she's got this huge Viking 6-burner gas stove.
And makeup here?
Oh, yeah. So, and she very seldom turns on the outside vent over the stove. But, you know, Mike, just the last year, because of being involved in LAQ, you know, I'm so focused on indoor air quality in my own home, a lot of entertaining and everything, is that I got an Intel air purification system. I put a brand new April air humidity system because humidity is so important, right? And then I also upgraded to the 3M Bluetooth monitored air filters. It's a lot more expensive. They're a higher quality filter, but it allows me to have a notice and monitor when that filter is starting to fail. So what is it doing? The Bluetooth just monitors back pressure, air pressure. But before that, it was a guessing game. I'd have to keep going down into the basement, pull up the filter and say, oh, it's still okay. Maybe it is, maybe it isn't, right? I hope that the HVAC contractors do something sooner than later, because to leave it, you know, the April Air thing was $500, right? To put the outdoor sensor in, you know, feed it into there, set it all up. You know, probably between air filtration, the filter, the humidity, that was $1,000, I suppose.
Good. Good. Thanks for the comments there. Okay. We have a question from the audience on the internet here. The question is, do you see any trends towards designing building HVAC systems with more granular zoning controls, such that smaller areas can be independently controlled more effectively? Mike, do you want to take on that from industry point of view?
From an industry point of view, I mean, there is a desire to get to more granular zone level control. And today we do have that capability through building integration systems. And so with the advanced controls, you now can get zone level. So you have for a large commercial building, medium-sized commercial building, most of those are multi-zone at this point and have thermostats within each one of the zones. Where the standards are really starting to head with the high performance building standards at ASHRAE is really starting to look at, okay, what is the guidelines to get us to the next generation of controls? And so you have developments within ASHRAE 42P, 189. Those are helping to move us towards these newer design trends that are more energy efficient and providing healthier air. We're not at the point yet where we've seen an uptake in the codes and standards from at the building level to drive into the contractors, those changes. Now, that being said, the White House challenge for decarbonization over the next decade is really going to set up a situation where the codes need to change in 3 cycles to meet that White House challenge. And there, I think there's going to be more interesting things to occur because of that driver for decarbonization.
Great, thank you, Mike. All right, I think, let me see who, I can stop sharing, maybe you can see who are on the website. Yeah, we still have many audience on the web, 17 participants there. I think we're running over time a little bit. Sorry that my time control is, is poor. And I hope this forum has provided some worthwhile information and create some also exchange between the academic and also the industry partners. I think probably next time we'll encourage more people come on site if possible. And actually, right after this, we have some networking activities in the lobby with some drinks and correct? Some snacks, snacks outside. So I encourage you to stay and then just talk with each other. And there's also a ping pong table there. If anyone would like to challenge me, I'd be most delighted. Okay, thank you all for your participation, and I look forward to see you again in next forum. Okay, thank you all.